Okay, so let's start with our first presentation from Team FTC 21229 Quality Control. They're a community-based team from Bellevue, Washington State, and they were part of the 2023 World's Winning Alliance and have won two Innovate Awards at Worlds. And today they'll be talking about the basics of inverse kinematics in robotics. Go ahead.
Okay, just testing my microphone. Can everyone hear me?
Yep.
Okay, I guess I'll begin then. Let's share the screen. Okay, and can everyone see my screen? Okay, nice. All right, so I'm going to be talking about the basics of inverse kinematics and robotics. I'm Rick from Team 229 Quality Control. And here's a table of contents. I won't go over it too into much detail. Okay, like previously mentioned, we're a community-based team in Bellevue, Washington, and this is a picture of us at Worlds last year. Okay, let's get started. So what is inverse kinematics? There's a formal definition, which is the process of calculating the joint angles in a mechanism such that the end position reaches a desired target position. However, you can also extend this definition to include translational parameters. For example, on your robot, you might have slides in addition to just arms. Right, so what are some use cases? Of course, you're going to need this in FTC whenever you're moving any mechanism to integrate a game element or to score. However, it's also prevalent in industrial usage, such as in these robot arms, where you have to, let's say, drill a hole in the chassis of a car. Additionally, there's also applications in computer graphics as well. I know many of you might be familiar with this lamp. Inverse kinematics is involved in these kinds of animations. Okay, so let's talk about degree of freedom analysis. In total, there are six possible degrees of freedom. You have three translational degree of freedom and three rotational degree of freedom. Basically, the translational degree of freedom are translation along each of the three axes, and the rotational degree of freedom are just rotation about each of these three axes. And you can look, let's see this specimen bar from Into the Deep last year. It has one translational degree of freedom in that it can slide along the bar, but it also has one rotational degree of freedom in that this specimens can rotate about this bar. For the samples in submersible, you might have two translation degree of freedom in that they can move side to side and along this direction, but also you can rotate around. So that's also one rotational degree of freedom. This ball and socket joint has three rotational degree of freedom, and this joystick has two rotational degree of freedom, although it has constraints in that it can't turn too far. Okay, so how do we determine whether inverse kinematics is needed, and if so, what kind? Basically, you check whether there's multiple solutions. Um, you first analyze the degree of freedom of the mechanism and that of the end position, and you compare, and this gives you the result. For example, let's say we just have one arm. It's a pretty poorly designed arm, and it can only rotate through one rotation degree of freedom. If I'm at where this blue dot is, it can reach it. However, if I'm anywhere else, this arm is never going to be able to reach the target position. So that would have lower degree of freedom. And this usually means that you have a design flaw. Or if you have, let's say, two rotation degree of freedom and two translation degree of freedom, in that I can move my mouse anywhere. I don't know if you guys can see it. But this basically means that this arm can usually reach wherever your mouse is or the target position is. And there are two solutions. And these two solutions are analogous. You can see that this red solution is basically just the gray solution, but flipped over. However, if you have higher degree of freedom than the end position, as in the bottom two, you notice that there are multiple possible solutions for the same target position, right? These are two different configurations that can reach this blue dot. And this means that you need more advanced inverse kinematics algorithms along with decision making, like what configuration am I going to use? Okay, so let's talk about the trigonometry and vector-based method. This is normally used when you have the same amount of degrees of freedom in the mechanism and in the target position. And the main idea is to use trigonometry to break down each segment into its x and y components to get equations. So using a bit of vector math, you notice that the relative position from your first joint to the end position is equal to the relative position from the second joint minus the first joint, plus the end position minus the second joint. And then you notice that if you just cancel out J2 here, these two sides are equivalent. And then you can break each vector down into its x and y components. For example, on the left side, you can separate into EX and EY. While for J2 minus J1, you have this right triangle. And you notice that the x component is just the hypotenuse, which is L1, times the cosine of this angle, which is theta 1, to get this length. And then you can do it similarly for the other sides of the two right triangles. And notice that you usually know what EX, EY, and L1, L2 are. EX, EY, that's a position you want to go to. That's given. And then L1, L2, those are usually the different parameters in your mechanism that you can measure with a ruler or a meter stick, something like that. And what you want to know is the joint angles, right? Theta 1, theta 2. So you basically get by setting these two equal, you get two separate equations and two variables. And this is a system of equations that gives you one or two fixed solutions. You can use ChatGPT to solve this. Note that you don't need to find the exact answer. You just need the expression. Okay. One important thing to note is here to set the angle to relative angle relative to J1's angle, right? You want this smaller angle above rather than the entire thing. And you can derive these relative angles by subtracting them. The servo at J2 should be set to theta 2 minus theta 1, right? Using corresponding angles, you get that this small angle, this larger angle is equal to theta 1. And you can generalize this to multiple segments as well. You get that the servo angle at any given joint is equal to the absolute angle at that joint minus the previous one. Right, so let's generalize this. Um, Note that you don't have to stick with two segments. You can have an infinite number of segments. So you can just have as large of a summation as you want. You can also, if you have, let's say, a slide extension rather than a servo angle, you can set Li as a parameter, right? And then if it's like a fixed slide, you can fix one of these theta. However, if you have like a slide on a turret, you can set Li and theta I as a variable. And basically, you can get different kinds of equations that lead to your fixed solutions. However, note that if you have more variables than your equations, as some of you may be familiar with, if let's say you have one equation, two variables, you're going to have multiple solutions. And this does correspond to degree of freedom analysis, right? Because each variable corresponds to a degree of freedom. If you have more degrees of freedom in the mechanism, then you're going to have multiple ways of reaching that end position. Um, Another generalization you can make is that you can set additional conditions, such as the end orientation. You can set constraints at like what theta 3 should be equal to, right? And you can also extend this into 3D space because we live in a 3D world and robots operate in 3D using EZ and also the polar to Cartesian coordinate conversion. And you have these equations here. Note that it's not just simply cosine and sine, but rather you have to find the different lengths in this right triangle, you have to use these slightly more complicated equations. Okay, let's go through a work example. So let's say we have this intake, right? Horizontal slides. On the slide, there's a turret along with a virtual four-bar mounted on this turret, and we have a claw with a wrist at the end. So the question is, how do we determine the separate parameters such that we can intake a sample? Let's first do a degree of freedom analysis. Note that the intake has one translational degree of freedom, that's the slide, and two rotational degree of freedom, right? We have the turret and the wrist. Note that the virtual four bar will actually be fixed, which corresponds to 0 degrees of freedom, and I'll elaborate on this later. As mentioned previously, samples of submersible have two translational degree of freedom in that they can be anywhere, and one rotational degree of freedom in that they can usually rotate to any given angle. Okay, so let's look at the side view. So we're looking at this intake from the side. And basically, we only consider the y and z coordinates in order to find out what our virtual four-bar angle is. And we noticed that the only way to lower our claw to the ground is to use this virtual forebar, which means that if we take the height from the sample top to the slides, that's this side of the right triangle. And this is fixed because the slides will always be a certain height above the ground. And if you set this distance to d, then you get that d is equal to L2, that's a hypotenuse, times sine theta. And then you can manipulate these variables to get an expression for this virtual four-bar angle. Similarly, you can use a top view. Now we're looking from above to find the turret angle. Now we only consider the x and y coordinates. And once again, we notice that the only way to move this claw horizontally is to turn the turret. And you notice that L2 cosine theta is actually the length of J2, J3. Note that you don't just want to use L2 or the length of the virtual four bar. You want to use this length, which is a projection onto the horizontal plane, rather than this longer length. And once again, if you set this length equal to m on top, the relative x position, then you get an equation for it using this right triangle. You get that m is equal to the hypotenuse times the sine of the turret angle. And once again, you can use this to get a fixed equation or expression for theta. And you can usually plug this into the code and it outputs the angle you should turn to. Okay, now let's continue using the top view to calculate this slide extension along with the wrist angle. Once again, we only consider the x and y coordinates. And note that because we already found the virtual four-bar angle and the turret angle, we can now treat them as fixed. So now, if we assume the total displacement in this y direction, which is distance from J1 to E along the y-axis, let's let this be big D. You notice that this is equal to L1 plus the hypotenuse times the cosine of theta. Remember, adjacent over hypotenuse is cosine. And then you get an expression for D, which is that it's L1 plus whatever this length is times the cosine of theta. And you get an equation. You can also manipulate this equation by moving L1 to the side and D to the other side, and you can get the slide extension. And note that the wrist angle is just the sample angle, which is the angle you want to turn to, minus the turret angle. And you have to recall the formula for the relative angle. Are different. But some main takeaways are when you're dealing with this kind of scenario, you should usually analyze the cross section separately. Those are the XY plane, YZ plane, and sometimes XZ plane. Some other cases would be the cross section of the turret plane. So basically take the plane that contains the turret, and that's usually pretty helpful to work with. And you also should start by deriving the most strict parameters and then use those to derive the other parameters. In our example, the most strict parameter would be the virtual four-bar angle, right? And you notice that the wrist angle depended on the turret angle, which depended on the virtual four-bar angle because you had that projection. And also that depended on the height of the slides off the ground. So usually one parameter depends on another parameter, which eventually depends on a physical value. Okay, so now let's talk about kinematic discontinuity. So I mentioned earlier, if you have higher degree of freedom in the mechanism than your end position, you're going to have issues. The main issue is that it's difficult to choose which solution. Oh, wait, someone. Okay, so no one's asking questions. No, wait. Damn, how do I go back? Yeah. Okay, so let's say we have these two relatively adjacent configurations. Um, in that these two blue dots relative to the initial joint are in a similar position. However, let's say that we were to move this mechanism slightly. What if our mechanism suddenly jumped from this left orientation to the right orientation? This is pretty bad for your hardware. You don't want your mechanism jittering around back and forth because hardware requires these locally smooth solutions. You don't want these jumps. You can also visit this link if you want to play around with a fabric demo to visualize these kinds of jumps. Okay, so how do we solve this issue of kinematic discontinuity? Basically, there are multiple strategies. First is to apply an artificial constraint. For example, you might want the claw to always be parallel to the ground, or you can fix a joint angle, or you can basically make one of your segments of your arm like a dead arm, in that it must always be at a certain angle. The virtual forebar is a hardware way of accomplishing this, making the end of the virtual forebar always parallel to the starting point. A few algorithms include Fabric, CCD, and the Jacobian transpose method, which I'll go into later. Okay. Uh, the first algorithm is Fabric, which stands for forward and backwards reaching inverse kinematics. And here's the process. First, you move the end to the target position, and then you adjust the joints moving forward from end to base to maintain the original link lengths. You basically move it so that the previous joint and the previous joint position, along with it, the next joint are collinear, right? So each of these lines are collinear. Here's a video which I think will give a better visualization. So let's see the end position here. You basically move it forward, and then afterwards you repeat the same process, moving the mechanism backwards. You repeat this process over and over again until you get a nice approximation, um, which you can see over here. Okay. Additionally, if let's say your servo doesn't turn 360 degrees, as with many servos, you can also apply constraints on those joint angles as well. Okay. Next page. The next algorithm is cyclic coordinate descent. So this is basically similar to Fabric, but instead of moving the segments, you move you turn the joint angles instead. So you basically iterate through the joints, rotating them such that the end joint aligns with the desired end position. And I think a video might be okay. So it's hard to see here, but you're basically rotating each joint angle such that these 3 points are collinear, such that they align with the previous joint position, the end joint, and the target position, which is represented by this orange sphere. And once again, you can also apply constraints similar to in Fabric. However, if you notice over here, it's not actually approaching a good solution. This is because cyclic coordinate descent usually requires dampening to avoid this kind of curling behavior. Applying angle constraints to account for like hardware conditions is also a way to avoid this type of curling behavior. Okay, so now let's talk about Jacobian transpose method. I don't know if many of you are familiar with gradient descent in machine learning. Jacobian transpose method is a form of gradient descent. And the process is that first you calculate the error vector. This is the target position where you want the mechanism to go to, minus the end joint, which is where your mechanism currently is. Then you can compute the Jacobian matrix, which is basically a matrix that represents how much the end position moves with respect to how much you tweak each parameter or each joint angle. And you can derive this by simulating in the code what would happen if you were to move it ever so slightly. Um, how much would the end position change? And then you calculate this rate of change. And then you can get the Jacobian transpose, where it's just a fancy name for taking the Jacobian matrix and flipping the rows and columns. And miraculously, if you multiply this transpose by the error vector, you get a vector containing how much you should adjust each joint angle by. And then you add on this resulting vector to the joint angle vector, and then you get your new angles that you should move to. Okay, so which method should you use? Usually, Fabric converges faster and is simpler to implement. However, it has a certain degree of limitation when you're trying to achieve a certain end orientation. Cyclic coordinate descent, like I mentioned previously, has some curling behavior, and also might be slow to converge. However, it's relatively simple to implement. And the Jacobian transpose method is by far the most stable strategy. I believe it's the most commonly used, However, it also converges slower because you're taking small steps rather than discrete steps by moving through each of the joint positions. Jacobian transpose method is basically a trade-off in terms of accuracy. If you have smaller steps, that's going to take longer to converge. If you have larger steps, it might not necessarily be accurate. Okay, so now let's talk about some industry standards for motion. The first being URDF, which is the Unified Robot Description Format. This is basically like kind of like a file type for robots, and it stores many properties like mass, inertia, along with visual properties like shape and color. And basically, it stores all the information that you or industry professionals need for inverse kinematics for a certain mechanism. It also allows you to create accurate simulations and visualizations because of these properties that it stores. And then there's ROS, which is Robot Operating System, and Move It. Basically, ROS is a framework with tools, libraries, and conventions for robot software. And Move It, which is built on ROS, is the dominant framework for motion planning, kinematics, along with collision avoidance. Basically, everything you need to get a robot moving. And then usually in industry, you have 6 degree of freedom arms. I think you guys might know why this might be, which is that our 3D world has 6 degrees of freedom in that you need to achieve a certain end orientation, which is 3 rotational degrees of freedom, and 3 translational degree of freedom, in that you need to move to a certain position. Okay, and then I have a quick video of a 6 degree of freedom arm in FTC. And the inverse kinematics were used to reach this given position. Okay. So that's it. Are there any questions?
Okay. Um, we can get one in-person question if any of y'all have any questions. No. Okay. Great. Thank you so much for that presentation on inverse kinematics. If there's any questions in the chat, I think you can answer them in the chat as well, because we're running kind of behind. Okay. Sure.